Let's talk about an electrocyclic reaction that is extremely useful synthetically, the Diels-Alder reaction. Now it's useful because we can form a 6-membered ring which is then susceptible to further modifications. So we can start off with 2 individual components, what we'll see as the diene and the dienophile, and link them up to form this 6-membered cyclohexene. Before we get into any considerations or the mechanism of this reaction, you can tell there's already a pattern here. We're forming a cyclohexene, which may be variable at these 4 positions here. In fact, all 6 carbons could be variable. There could be other groups that are attached to the 6-membered ring at all 6 carbons. But the idea is that 4 pi electrons from the diene, all of these left compounds here, and 2 pi electrons from the dienophile, these molecules here, will link up to form 2 new sigma bonds, which are shown right here and right here in all of these 3 examples. So this is exactly why it's called a 4+2 cycloaddition. 4 pi electrons from the diene are involved with 2 pi electrons from the dienophile in a specific configuration that we will consider to form these sigma bonds, to form these rings. Let's look at a very simple example to contextualize the Diels-Alder. Now let's use 1,3-butadiene as a simple diene and ethylene right here. And the convention we'll use to number this is starting here at 1. So 1, 2, 3, this is carbon 4, 4 is attached to 5, 6 here is attached to 1. So what happens is, exposure to heat will cause the formation of our 6-membered ring, where the double bond occurs between carbons 2 and 3, and the sigma bonds, like we said, occurs between 4 and 5 and 1 and 6. Now to show that mechanistically, what we're trying to say is that the diene is actually the electron donor, not necessarily nucleophilic, but what happens is the pi bond between 3 and 4 will donate electrons to carbon 5, like this. Because of arrow pushing, 6 will attack 1, and the pi bond reestablishes from 1 to 2 over to 2 to 3, and we see that in the product. And we should mention the reaction is theoretically reversible. So this is a simple example. So how do we link these 2 together? Now we need to dive into molecular orbital theory. We're saying that the highest occupied pi molecular orbital of the diene links up with the lowest unoccupied pi molecular orbital of the dienophile. In other words, HOMO and LUMO. And this example is perfect to understand that orbital overlap, because ultimately to form a sigma bond, we need some sort of in-phase orbital overlaps, which is the foundation of bond formation. The HOMO for the diene is always referencing the highest energy electrons in which we are maintaining bonding interactions. That's what this occupied means. So there may be antibonding interactions due to phase change, but it's critical to understand that they are the highest possible energy electrons while still maintaining bonding interactions. So let's draw out butadiene and separate out all 4 p-atomic orbitals. It turns out for 1,3-butadiene, we have a bonding interaction here on the top and a bonding interaction here on the bottom on the right side. Now we show that with 2 different colors to show phasing, like so. This region in the middle is called a node. No electron density is found here because of the phase change of these 2 individual pi bonds. And we call this molecular orbital pi 2. Pi 1 would be all reds on the top, where we can kind of use a hose analogy. The water flows throughout the entire compound. Here we have a pinch in the hose, and that's because of the phase change. So that's why we have these 2 individual pi bonds. Remember, it's important to note that these are occupied. Now for ethylene, let's draw in the LUMO right here. Ethylene is a simple example because if we draw in the 2 p-atomic orbitals that are contributing to the molecular orbital, it is quite simple. If we put 2 blues on the top, like this, of course the opposite phase on the bottom, we can show the pi 1 molecular orbital for ethylene, total bonding interaction. Now to show LUMO, it would make sense to flip the phasing. So some sort of catalyst like heat is causing this phase change, where now we have red on top, let's say on the right side, and blue on the bottom. And again, we have a node in the middle to signify no electron density. Now what's the point of drawing all this out? Well, the idea is to use molecular orbital theory to show where the 4-5 and 1-6 sigma bonds are coming from. Now we can see that the in-phase overlap from carbon 4 to carbon 5 and carbon 1 to carbon 6 is quite obvious. Now if you imagine the dienophile is mobile and we just keep the diene static, you can imagine that this dienophile is approaching from the bottom and just parks itself right here. We can see then that between 1 and 6 and 4 and 5, the proximity is so close that we can form that sigma bond between 1 and 6 and 4 and 5. So we have this interaction here in this region and another interaction in this region. And it's this overlap that constitutes the sigma bond. So with a simple example, we've shown why the HOMO and LUMO, as a part of the diene and dienophile respectively, are critical for the Diels-Alder. It's this heat catalyst that is promoting these electrons to a higher energy state. The HOMO is the highest occupied pi molecular orbital in which all pi bonds are occupied. The LUMO is very similar to the HOMO, except there is one additional node usually, and we have an unoccupied molecular orbital. We'll see that in a more advanced example. So let's try to illustrate example 3. 1,3-butadiene is quite straightforward if we draw in the molecular orbital. This is the pi 2 HOMO. Again, the diene requires the highest occupied pi molecular orbital. And we see that here. An occupied pi bond here and here. Overall, this is bonding because we have 2 bonding interactions and only 1 anti-bonding interactions here where we see the node. So if we try to classify a ratio for 1,3-butadiene, it's a 2-to-1 bonding to anti-bonding interaction. The bonding outweighs the anti-bonding. Now what about the LUMO? This is maleic anhydride, and this molecular orbital is quite confusing. So let's look at a simpler example and then translate it over. We said the LUMO needs to have greater anti-bonding interactions than bonding by a factor of 1. So 3-to-2 anti-bonding to bonding in this case. Let's use another molecule that also has 6 pi electrons, such as hexatriene. In the case of hexatriene, the pi 3 molecular orbital is the HOMO and pi 4 is the LUMO. If we have 6 pi electrons, we have 6 pi molecular orbitals, but it just happens that 3 and 4 are the ones that are the HOMO and LUMO. So for the highest occupied molecular orbital, we need more bonding interactions than antibonding. In this case, for hexatriene, it's a 3-to-2 ratio. So it makes sense that the LUMO would be a 2-to-3 ratio. Let's see if we can prove that with molecular orbital theory and drawing out these diagrams. So for the HOMO, we need to maintain bonding interactions. We have 6 p atomic orbitals here, and we understand that a pi bond involves 2 p atomic orbitals. So if we divide all 6 of these p atomic orbitals by 2, we get 3. So 6 divided by 2 gives us 3, which means we need 3 bonding interactions, like we said, 3 pi bonds. We can think of it as 3 individual pi bonds. So let's shade in this diagram to show that. Now we need to designate the phase change, one node right here, and another one right here. This is our antibonding interaction. So we've shown a 3-to-2 ratio. How do we get a 2-to-3 ratio for the LUMO, which is exactly what we need for maleic anhydride? Well, we need to reduce the bonding interaction by 1, so 2 bonds. On top of that, we need 3 antibonding interactions, meaning 1 extra node, 3 nodes. So it turns out it looks like this. To maintain an aspect of symmetry, we put the unoccupied sites on the edge. Let's put one red up here, and then immediately change the phase to show our first bonding interaction. We can then change the phase again and show a bonding interaction on the top, and then one last phase change, our third one, like so. And again, let's make sure we have 3 nodes. One right here, one right here, and one right here. So 3 antibonding interactions, 2 bonding interactions. This is our LUMO. Now let's keep this molecular orbital in mind and look at maleic anhydride, which is really the same thing. We need 3 antibonding interactions and 2 bonding. And we see that right here, a bonding interaction here, as well as right here. And to designate our three antibonding interactions, we have three nodes, here, here, and here, just like with hexatriene. So again, why are drawing these diagrams useful? We're trying to show that a sigma bond can form between 4 and 5 and 1 and 6, just like with our simple example with ethylene. Same thing here. We're trying to form the 4, 5, and 1, 6 bond by the overlap of in-phase p orbitals, which is what we're calling the primary interaction here in green. So we see that as maleic anhydride is approaching butadiene, it just so happens from the bottom, an in-phase overlap occurs between the carbon 5 blue up and the carbon 4 blue down. It's an in-phase overlap. The same with carbon 6 and 1, except here it's red. Now what about this black interaction here, which will help us understand the stereochemistry of the product? What we're showing here implicitly in all these examples is that if a group is leading into the diene, like this aldehyde, like this ester, and like this anhydride, they're all being flipped down in what's called the kinetic product. This ester is being flipped down, this aldehyde also, and this anhydride portion is being flipped down here, and we're seeing that right here also, what's called the endo product, the Endo Rule. Why does this happen? What's this secondary overlap? It's a favorable transition state, a stable transition state, which leads to the less stable product. What happens is, this individual pi bond right here has blue up, and between 3 and 4 it's blue down. So on top of an interaction between 4 and 5, this carbonyl carbon right here and here also contain the same phasing with carbon 3 and carbon 2. You get another secondary overlap. Again, it's favorable. We have a stable intermediate leading to what may be the less stable product, the kinetic product. Sometimes the kinetic product is the thermodynamic product, in which there is no thermodynamic control on the reaction. But generally speaking, the stabilized intermediate as a result of secondary overlap, shown here in black, is the reason why the electron withdrawing group leads. It's favorable, which is always why the first product that is formed most readily, most quickly, as a result of the stable intermediate is the kinetic product, in which we have the electron withdrawing group endo, pointing down. 1,3-butadiene has one node, and we see that here. 2 reds up, 2 reds down, and we see that here. This is kind of a view from the bottom. Maleic anhydride, 2 blues up, 2 blues down, and we see that here. 2 blues up, 2 blues down. This oxygen is leading, it's pointing into the page. And because it's LUMO, we have the unoccupied sites here and here, and that's shown here. Now let's look at this from the side. Again, butadiene, 2 reds up, 2 reds down, this is the HOMO. And here's maleic anhydride, the LUMO. What we're trying to show is not the individual p atomic orbitals that we see here, but we kind of merge them into the pi bonds that we're trying to express here. And you can clearly see a very favorable interaction because of the phasing of these molecular orbitals. This is exactly why we need the HOMO and LUMO to begin with. The diene lies above, and the dienophile kind of leads from the bottom into the diene. So we have this favorable overlap. The blues overlap favorably, and so do the reds, because of this idea of phasing. So it is this exact overlap that helps contribute the 4, 5, and 1, 6 sigma bonds, as well as this secondary overlap shown in black. Again, it's favorable, which is why all of these electron withdrawing groups are leading. So this is the theory behind the Endo Rule. The electron withdrawing groups that lead will be forced to flip down. And we see here with maleic anhydride how it kind of does a front flip and flips down.